So let's start with this chapter with the first part, isomorphism. So just a gentle reminder that the chapter is called linear maps. So the first part is going to be about isomorphisms. Okay. And as we have seen in the introduction, this chapter is going to be divided into two parts. Into this, as we have seen in the introduction, this part, which is the first part of the chapter, is going to be divided itself into two sections, okay? And in the first section, we will see definitions and examples. And examples. So basically the plan is in this video, okay, in this current video, I will do part A and part B, the theoretical part. So we'll see definitions, some examples, theorems, lemmas. Then in the second video, I'm going to do a tutorial, okay? So let's continue. And let's start with the definition, okay? What is an isomorphism? Definition. Okay. So let me write an isomorphism. So remember we are dealing with linear maps. So an isomorphism between two vector spaces. Okay, between two vector spaces. We are going to call them V and W. Is a map defined as follows. Okay, we are going to call that map F, defined from V to W, such that that map is one. Okay, let me write this. Is important what I'm going to write next. That map is number one, a correspondence. Okay, is a correspondence. I will explain shortly what we mean by correspondence. And two, the map preserves structure. Okay, and preserves structure. Okay, so I say so that the map is a correspondence. By correspondence, we mean that F is a one-to-one, is one-to-one, and F is onto. So by correspondence, we mean the map is one-to-one and is onto. Preserve structure basically means it preserves addition and scalar multiplication. So preserve structure means if we have two vectors, v1 and v2, from both of them are elements from V. Then we have number one preserves addition. Okay, f of v1 plus f plus v2 should be equal to f of okay, let me keep it short here, and in the next part I will show you the how to. Okay, so basically when we say it preserves structure, what am I writing here? I say structure. No, It preserves structure. Preserves structure. So basically by preserving structure we mean it preserves vector addition, vectors addition, and it preserves scalar multiplication. Okay, so that is what we mean by an isomorphism. So an isomorphism is a map, a linear map between two vector spaces, and that linear map must meet these two conditions: correspondence and preserve structure. So first of all, let's see what the word isomorphism means. It doesn't matter, but isomorphism can be split into two words. We have iso, okay, it's a Greek word which means equal, and morph, which means shape or form or map, if you want to. So isomorph means equal shape, or isomorphism means equal shape, equal form. So we will see in section 2 what is equal. So basically there is something equal between the space V and W. Okay, so we will see what is equal. As you can see, V and W are actually different letters, but there is something deeply, or something we can use to characterize the sameness, or the equalness of V and W, and you will see in section 2 that is the dimension. Okay, so basically if V is isomorphic to W, it means they have something equal. What they have equal is the dimension, and it's such a beautiful theorem. Okay, so V is isomorphic to W if they have the same dimension. So beautiful. We will see it shortly. So we write, let me finish the definition. Okay, we write V is isomorphic to W. Okay, so that means V is isomorphic to W. That's how we write it, or we note it, and yeah, we will see shortly. And as you can see, there is a difference between the word isomorphism, a subtle difference, and homomorphism, because iso means equal, and as you will see shortly, homo kind of means equal, but it actually means same. So there is a subtle difference, and we will see that subtle difference shortly. This is a very, very interesting chapter. I love linear maps. I love this chapter. Okay, so that's the definition. And what I'm going to do here, probably I will go to the next page and we will see how do we prove that a map is an isomorphism. Yes, I just gave you the definition, but what do we actually mean by a map is a one-to-one? Okay, I will show you shortly. So here, let me split the screen into two. I will show you the how to. Let's call it how to. Okay, so we are going to see how do we prove that a map is an isomorphism. Okay, so to verify that map F defined from V to W is an isomorphism. Okay. We have to go through the following 4 steps. Okay. Number 1, yeah, I'm going to change color here. Number 1, we need to prove correspondence. And by correspondence, we need to show 2 things as well. So let me change the color. So I don't know if I want to call it, I'm going to call it A so that I don't confuse people, okay? A, we need to show that F is 1 to 1. So what do we mean, or how do we prove that F is 1 to 1 is as follows, okay? First of all, we will assume uh, 2 vectors from the domain V1, V2. Okay, they are from the domain spaces. So we will use 2 vectors from the domain spaces, and such that, okay, we will assume that F of V1 equals to F of V2. Then, and the proof, okay, derive that will lead to V1 equals to V2. So basically, if you have 2 elements from the domain space and we look at their images from the codomain space, if their images are the same, that means those 2 elements from the domain spaces are also the same. Okay, so basically we can't have, basically what it means is every single element from the domain space has a single image from the codomain space. So basically we can't have an element from the codomain space that is linked to 2 elements from the domain space. Is that okay? So it's 1, 2, 1. Now we need to show that it is onto B onto F is onto. So how do we prove that F is onto? Here we will use an element from the codomain space, let W be an element from the codomain space, and we need to find an element, okay, from the domain space that maps to W. So, and we need to find V, an element V, a V from the domain space such that F of V equals to W. Okay, so that is how we prove correspondence 1 to 1 and onto. And I will do shortly in the next video a tutorial. Okay, so if you don't get it yet, don't worry, I will do a tutorial shortly. So basically, as I said, to prove that a map is an isomorphism, we need to prove 2 main things: correspondence, and the second thing is preserved structure. Need to prove preserves maybe let me write it on the same line. Okay, so 2, need to prove that F preserves structure. And by preserving structure means we mean that F preserves vectors addition. You need to prove that F preserves vectors addition. Okay, so by preserving vector addition we means, or by F preserved vectors addition, we mean that for all, okay, V1 and V2 from V, okay, we have, okay, oh, I should change color. Sorry about that. So basically, I was saying for all V1 and V2 from the domain space, we have to show that F of V1 plus V2 is equal to, or must be equal to, F of V1 plus F of V2. Then we can conclude that F preserves vectors addition, okay? And finally, we need to prove that F preserves scalar multiplication. Preserves scalar multiplication. So here we need to say that for all V, okay, from the domain space, and for all R, or for any scalar R from which is a real number, okay, we have F of R dot V equals to R multiplied by dot scalar multiply F of V. Okay, that's how we prove scalar multiplication. So I'm going to give a small note here. Okay, let me change color because this is just a short note. Okay, let me actually write this note here from the definition. Okay, so note, every space, okay, here I just want to highlight that every space is isomorphic to itself under the identity map. Okay. Every space is isomorphic to itself under the identity map. Under the identity map. Okay. So let's continue with our how to. So basically, actually, I should stop here and give the tutorial. Pick a function and to show that it is an isomorphism. But I prefer to do all the theories here and do the tutorial in the next video. So you have two choices. Either you stop the video here and go to next video to look at the tutorial, okay? So a concrete example of how to prove that function is an isomorphism, and then come back and watch the rest of the video. Or you can continue this video till the end and then watch the next video, which is going to be the tutorial. Okay, so let's continue. I would like to go to the next page and batch 3. Let's look at another definition. Okay, so another definition here. 3 definition. Okay, what do we call a linear map that has the same space for the codomain, the same codomain space as the domain space. So a function, a isomorphism, an isomorphism defined from V to V, for example. Okay, it is called an automorphism. So let's look at the definition. So an automorphism, okay, an automorphism is an isomorphism, okay, of space with itself, of a space with itself. So basically F defined from V to V, okay, is an automorphism. So let's continue. Part 4, let's see some examples of automorphism. Examples of automorphism. Okay, first of all, we have the dilation map. Okay, let me write it here. A dilation map. So a dilation map. So what is a dilation map? Okay, let's call a dilation map, let's call it DS, defined of course from R2 to R2, okay, from V to V. Here let's use R2 to R2. That multiplies any vector by the scalar S. So map, okay, dilation map multiplies all vectors from the domain R2, okay, by a known all vectors. It multiplies all vectors by a known 0 scalar 0 scalar S. So it is called an automorphism of R2. Okay, is called, okay, for example, okay, an automorphism of R2. So I'm not going to repeat myself because this is an example of an automorphism. So yeah, let me give you a quick graph here. Let's say instead of DS, let's use D2, a dilation map that multiplies all vectors from the domain space by 2, for example. So let me give you this quick example. Okay. So let's say we have our x 1, 2, 3, 4. Yeah, let's have 2 here and 1. So this is going to be our v1, 2, 1. So v1, let's have v1 here and 1, 2, 3, 4, 5, 6, and let's go with the v2, which is 1, 1, 2, 3. Okay, let's go with 3 here. So that's 3. That's 1. So we have v2 here, v2. Okay, so if we apply a dimension map to this space, okay, d2, let's multiply all vectors by 2. It will give us the following results. Okay, so we have 1, 2, 3, 4, 4 there, 1, 2, 3, 4, 5, 6, and 6 there. So we are going to multiply v1 by 2. So x is going to be 4 and y is going to be 2. For v1, our new v1 is going to be v1 in the codomain space, okay, the image of v1 under the dilation. This dilation map is going to be this new vector v1, and the second vector is x is going to be 2, y is going to be 6. Sorry. Okay, so this is going to be v2. So under this dilation map d2, okay, we are still in R2 here, and here the R2, okay, 2-dimension real space. So this is going to be the image of these two vectors under this dilation map. Let me give you another example of an automorphism, and then we will stop here. So we have a rotation. Rotation is also an automorphism. So a rotation or turning map, we can also call it a turning map, okay? Turning map is defined as follows. So t theta, so it's going to be every vector is going to be rotated with at the angle theta from R2 to R2, okay. Rotates all vectors through the angle theta. Okay, here as well, let me give you a quick example. So x here, y, and this is for my face different from x. They look quite similar. Let's say we have a vector v here, and under, for example, the rotation, this rotation map t pi over 4, okay, we are going to rotate v through the angle pi over 4, 45 degrees, okay. So x here, y here, and this is our pi over 4, and our new vector is going to be something like this. This is our new vector. So through the angle pi over 4. Okay, so this is theta. Pi over 4. We call it pi over 4, not theta, even though they are the same. So pi over 4. This is our new V. So basically that is the end of this first section, section A. Okay, I'm going to continue on the next page with section B. So in section B, as we have seen, this is going to be titled Dimension Characterizes Isomorphism. Characterizes isomorphism. So morphism. Okay. So here we are going to see some lemmas and theorems. Lemma 1 is going to be lemma. Going to see plenty of some beautiful lemmas and theorems. The inverse of an isomorphism is an isomorphism. So basically, the inverse of a map that is an isomorphism is also an isomorphism. That means it's one-to-one, onto, preserves addition and scalar multiplication. Okay, so as I have said, I won't give formal proofs to lemmas, theorems, corollaries. I will sometimes do some example to illustrate those lemmas and theorems. Okay, but if some of you need formal proofs, you can just email me and I will provide you a short video about some formal proofs. Okay, so our lemma is the inverse of isomorphism. So morphism is also an isomorphism. Okay, and now let's have a look at this very important theorem, okay, about isomorphism. Theorem. I love this theorem. It says the following: isomorphism is an equivalent relation. An equivalent relation between vector spaces. So what do we mean by equivalent? So I'm going to highlight this word, maybe with green. Okay, equivalent relation. So I won't give you a formal proof, but I will give you some notes. By how do we prove an equivalent relationship? To prove an equivalent relationship, we need to prove these three things. Okay, we need to prove that the relationship is a reflexivity relationship. Reflexivity. So basically, if we pick two objects, or here in this case two vector spaces, V and W, reflexivity means for this one, V is related to itself, or W is related to itself. Okay, and number two, we need to prove symmetry. We need to prove that the relationship is symmetric. It's a symmetry relationship. So V If V, we pick two vector spaces V and W. If V is related to W, that means W is also related to V, okay? That's symmetric relationship. And number three, we have transitivity. So basically it means that if V is related to W, then W related to U, another space U, then V is related to U. Is that okay? Okay, so let's continue. Number three, oh, this is my favorite one. Basically, I love all theorems here. But this is my all-time favorite. It says, it's so simple and yet so beautiful. Okay, it says vector spaces. That's what I was saying at the beginning. Okay, vector spaces are isomorphic if and only if they have the same dimension. Oh, the same dimension. Okay, so to see if two vector spaces are isomorphic, what you have to check is to check their dimension. So if you don't know how to find the dimension, don't worry, we will see it shortly. So this is my all-time favorite theorem of isomorphism. Okay, so let's continue. We have let's see another lemma. Another lemma. Okay, if, okay, so basically that's a consequence of what you have just said, or another way of saying what we have just said in the previous theorem. If spaces are isomorphic, then they have the same dimension. Same dimension. It's good. Another lemma. Another lemma says basically these two lemmas are just our theorem split into two, okay? So basically it's going to be the converse. If the spaces have the same dimension, then they are isomorphic. If, so it's the converse of the previous lemma. If spaces have the same dimension, then they are isomorphic. Isomorphic. Okay, then let's have a look at our final concept today, which is corollary. It says the following. It says that each finite dimensional vector space is isomorphic to one and only one of the Rn. So it's basically the canonical, I can say, a representation of an isomorphic vector space. Okay, so each finite dimensional vector space is isomorphic to one and only one of the Rn. Okay, so we will stop here. This is going to be the end of this chapter, this part, and I will see you in the next video. Okay, thank you.